Welcome to this complete Probability Masterclass video. Whether you're building a foundation from scratch or gearing up for upcoming exams, this comprehensive tutorial covers everything you need to know about probability theory and its applications. In this video, we'll walk step by step through the introduction to probability, Venn diagrams, the addition rule, conditional probability, probability tree diagrams, dependent and independent events, and Bayes' theorem. After covering all the core theory, I'll put your skills to the test with 3 detailed practice modules in which you'll find 11 sample probability questions with a full solution. Because this is a masterclass, feel free to pause, take notes, and work through the problems at your own pace. All the video chapters are listed down in the description below, so you can easily jump straight to any topic or practice section you want to review. Let's get started. In this video, we'll explore the key ideas that form the foundation of probability: experiments, outcomes, sample spaces, events, and or not logic, theoretical probability, relative frequency, bias, and how to find the probability from data using a histogram. In probability, an experiment is any action or process that produces a result, but we can't know that result for sure until it happens. Examples of this would be rolling a die, flipping a coin, or drawing a card from a pack of playing cards. When you roll a die, you don't know which number will appear. That uncertainty is what makes it an experiment. An outcome is a single possible result of an experiment. And so examples of outcomes would be rolling the number 4 when you roll a die, getting a heads when you flip a coin, or drawing the Queen of Hearts when you draw a card from a pack of playing cards. If you roll a die and it lands on a 4, that specific result, the 4, is the outcome. The sample space is the set of all possible outcomes of an experiment. So when we roll a die, we may get a 1, a 2, a 3 or 4, a 5 or a 6. And this is the sample space. When we flip a coin, the results could be a heads or a tails. And again, this is the sample space. Every outcome must belong to the sample space. For example, if the outcome is 4 in the die roll, it fits neatly inside the sample space of all die roll results. An event is a collection of outcomes from the sample space. For example, the event of rolling an even number in a die roll includes the outcomes 2, 4, and 6. When we say A and B, we mean both events happen at the same time. So if we have an experiment where we draw one card from a pack of playing cards, event A could be that we draw a red card, and event B could be that we draw a card that is a king. So A and B would be a red king, so that would be the King of Hearts or the King of Diamonds. And so for an outcome to be in A and B, it must satisfy both conditions. When we say A or B, we mean the outcome is in A or B or in both. Let's say we have an experiment which rolls a die, where event A is where the outcome is greater than 4. So the possibilities are 5 and 6. And event B is when we roll an even number. So the outcomes could be 2, 4, or 6. And so A or B includes anything that meets at least one of the conditions. So we could have 2, 4, 5, or 6. The word not refers to the complement of an event. So if we have an event A, this is everything in the sample space that is not in A. We calculate it using the formula where the probability of not A is equal to 1 minus the probability of A. And so if we have an experiment where we flip a coin, and event A is flipping a head, then the probability of A is equal to a half. And so the probability of not heads, which is tails, is also equal to a half, as it's 1 minus a half. Theoretical probability is based on logic and assumes all outcomes are equally likely. We can use the formula where the probability of success is equal to the number of successful outcomes divided by the total number of possible outcomes. Let's look at an example of this. Suppose we roll a fair 6-sided die and we let event A be rolling an even number. So in this case, the successful outcomes are 2, 4, and 6. So there are 3 successful outcomes. And the sample space here is rolling a 1, a 2, a 3, a 4, a 5, or a 6. So there are 6 possible outcomes. So the probability of event A is equal to the number of successful outcomes, which we've seen is 3, divided by the total number of possible outcomes, which we've shown is 6. So we have 3 divided by 6, which is equal to a half. If you'd like to support the channel, you can now become a member to get early access to every video. To join, you can use the link displayed at the top of the screen or just hit the join button right below this video. Sometimes results don't match what we expect, not because of randomness, but because something is biased. Bias means the experiment is not fair. Some outcomes are more likely than others, not because of chance, but because of the way the experiment is set up. So let's take a look at an example. If we have a coin heavier on one side and it lands on tails more often, the theoretical probability says that if we have event A, which is flipping a heads, the probability of A is a half. And if we have event B, which is flipping a tails, then the probability of B is also a half. But in practice, tails might appear 70% of the time. And in this experiment, the coin is biased. It doesn't give each outcome an equal chance. In real life, we often estimate probability by observing what actually happens. This is called relative frequency. This is given by the formula where the probability of success is equal to the number of times an event occurs divided by the total number of experiments. If we have an experiment where a student flips a coin 50 times, and in this experiment, the student flips heads 28 times, and flipping heads is seen as a success, the probability, therefore, of flipping a heads is given by the number of times this event occurs, which in our experiment is 28, divided by the total number of experiments, where the total number of experiments is 50, as the student flips a coin 50 times. So in this case, the probability of flipping a heads is equal to 28 divided by 50, which equals 0.56. So in theory, the probability of heads is 1/2, but in an actual experiment, we might get something slightly different, like 0.56. The more experiments we do, the closer the relative frequency usually gets to the theoretical probability. Now let's look at an example where we collect data, display the results on a histogram, and use this to calculate the probability. Imagine we surveyed 50 employees about their daily commute times, and we want to find the probability that a randomly chosen employee commutes less than 20 minutes. The data is shown here in a table, where we have a range of commute times in steps of 10, together with the frequency a commuter achieves a commute time within the various ranges. And so using this data, 5 commuters commute in less than 10 minutes, 15 commuters take between 10 and 20 minutes, 20 commuters take between 20 and 30 minutes, 8 commuters take between 30 and 40 minutes, and 2 commuters take between 40 and 50 minutes. We can plot this data using a histogram where we have commute time in minutes on the horizontal axis and frequency on the vertical axis. So here we have a question on relative frequency, where the probability of success is a commute time of less than 20 minutes. And this is given by the total number of times the event occurs, so that's a commuter commuting in less than 20 minutes, divided by the number of experiments, which is the sum of all the observations shown in the frequency column in the table. And to find this probability, we need to look at the ranges that fit less than 20 minutes. So that's the first 2 bars on the histogram shaded in blue. The first bar has a frequency of 5 and the second has a frequency of 15. Next, we can sum those frequencies together. So we have 5 plus 15, and this gives us 20 employees that commute in a time of less than 20 minutes. Now, we can divide this by the total number of observations shown in the frequency column of the table. So if we sum these, we have 5 plus 15 plus 20 plus 8 plus 2, and this gives us 50. So 20 divided by 50 gives us a probability of 0.4. And in terms of percentages, there's a 40% chance that a randomly selected employee commutes less than 20 minutes. Let's now look at what happens if we don't have a table of data, but just have the histogram. How do we go about calculating the probability? Well, the good news is that we use the same formula as before, where the probability of success, which in this case is a commuter commuting in less than 20 minutes, is the number of times the event occurs divided by the number of experiments. To find the number of times the event occurs, we find the area of the blue shaded region, which is 5 multiplied by 10, the area of the first bar, plus 15 multiplied by 10, the area of the second bar. And to find the total number of experiments, we find the total area under the histogram shown by the green region. So we sum the area under each bar. So we have 5 multiplied by 10 plus 15 multiplied by 10 plus 20 multiplied by 10 plus 8 multiplied by 10 plus 2 multiplied by 10. And this ratio gives us the probability. So we have 200 divided by 500, which is equal to 0.4. And so the probability that a randomly selected commuter commutes to the office in less than 20 minutes is equal to 0.4. So now we've looked at the theory, let's look at some challenges to consolidate our knowledge. So in this first challenge, we want to find the probability of rolling an even number on a fair die and landing on tails when we flip a coin. If you'd like to play along, pause the video now. So let's take a look at how we work this out. So on a standard die, we have 6 faces, 1, 2, 3, 4, 5, and 6. And 3 of these are even numbers, 2, 4, and 6. So the probability of rolling an even number is 3 chances in 6. And so the probability of it being even is 3 divided by 6, which is equal to a half. And when we flip a coin, there are 2 sides to a coin. So we have a heads and a tails. So to flip a tail, we have 1 chance in 2. So the probability of tails is 1 divided by 2, which is equal to a half. So now let's look at the probability of rolling an even number on a dice and flipping a tails. When we see the word "and," we associate it with a multiplication sign. Now we know the probability of rolling an even number is a half, and we know the probability of flipping a tails is a half. So we multiply these 2 numbers together and we get a quarter. So the probability of rolling an even number on a die and landing on tails when we flip a coin is a quarter, or 0.25. In this next challenge, if we draw a single card from a standard deck of 52 cards, what's the probability of drawing a card that is a king or a heart? If you'd like to play along, pause the video now. So in this one, let's find the probability of drawing a king. So in a standard deck of 52 cards, there are 4 kings. So we have 4 chances in 52 of drawing a king, which is 4 divided by 52. And in a standard deck of 52 cards, there are 13 cards marked with hearts. There are 13 out of 52 chances of drawing a heart. So the probability of drawing a heart is 13 divided by 52. When we look at the probability of drawing a king or a heart, when we see the word or, we associate this with summing the 2 probabilities. So the probability of drawing a king is 4 over 52, plus the probability of drawing a heart is 13 over 52. We then have to subtract 1 over 52. So why do we do this? Well, we do this to avoid double counting. When we count the 4 kings, we're counting the king of spades, the king of clubs, the king of diamonds, and the king of hearts. When we count the 13 hearts, we're counting the ace of hearts, the 2 of hearts, the 3 of hearts, all the way up to the king of hearts again. And so because the king of hearts belongs to both groups, it gets counted twice. And so subtracting 1 over 52, which is the probability of drawing a king and a hearts, corrects this mistake, so that every card in our target set is counted only once. So the probability of drawing a king or a heart is 4 divided by 52 plus 13 divided by 52 minus 1 divided by 52. And this gives us a probability of 16 divided by 52. And in this third challenge, let's calculate the probability that after rolling 2 die, the sum of the numbers shown on each is not 7. And if you'd like to play along, pause the video now. When we roll 2 die, we get a sample space of 6 multiplied by 6, which gives us 36 possible outcomes. And of those outcomes, we need to look for the combinations that add up to 7. So we have 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. So there are 6 combinations that add up to 7. So the probability of rolling a 7 is equal to 6 divided by 36. So there are 6 chances in 36. And this equals 1/6. Now, to find the probability of not rolling a 7, we use the complement rule, which is 1 minus the probability of rolling a 7. And this equals 1 minus 1/6, which equals 5/6. In this next challenge, we want to map out the entire sample space, so all possible outcomes, and calculate the probability of getting exactly 2 heads when we flip a coin 3 times. If you'd like to play along, pause the video now. When we flip a coin 3 times, the different outcomes we get are known as the sample space. So in this experiment, when we flip a coin 3 times, we could get heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. So in this experiment, there are 8 possible outcomes. Now we want to calculate the probability of getting exactly 2 heads when we flip a coin 3 times. And so if we look at all the possible outcomes in the sample space, there are 3 outcomes that produce this result. They are heads, heads, and tails, heads, tails, and heads, and tails, heads, and heads. And so in this experiment, there are 3 chances out of 8 outcomes of getting exactly 2 heads when we flip a coin 3 times. So the probability of getting exactly 2 heads when we flip a coin 3 times is equal to 3 divided by 8, or 3/8. When we study probability, we're trying to measure randomness. But before we can calculate a single fraction, we need to map out every single thing that could possibly happen. With probabilities, we do this visually using a Venn diagram. Think of this rectangle as a boundary line around our entire mathematical universe. We call this the sample space or universal set, and it's denoted by a U or an S outside of the rectangle. Every single possible outcome of an experiment lives inside the rectangle. To illustrate this, let's look at an experiment where we roll a fair six-sided die. The possible outcomes are the numbers 1, 2, 3, 4, 5, and 6. These numbers are our sample space, and these numbers fit inside the rectangle. Now let's look at an event. An event is simply a specific condition or a collection of outcomes that we want to track. On a Venn diagram, an event is represented by a circle. Let's define two specific events for our die roll. Event A is rolling an even number. That means that circle A wants the numbers 2, 4, and 6, as these are the possible outcomes of event A. Event B is rolling a prime number. That means circle B wants the numbers 2, 3, and 5, as these are the possible outcomes of event B. Look closely at those two lists. The number 2 is both even and prime. It satisfies both conditions simultaneously. If we put it in circle A, we lie about circle B. If we put it in circle B, we lie about circle A. This is why the circles must overlap. The intersection in the middle is the space for outcomes that belong to event A and event B. So what about the number 1? It's not even and it's not prime. So it's banished to the outer space, sitting inside the rectangle but completely outside both circles. Now, looking at specific outcomes like 2, 3, or 4 is fantastic for visualizing where things live. But when we want to calculate actual probabilities, we need to translate our thinking from individual listings to counting frequencies. A frequency is simply a count of how many items live inside a space. Let's rub out these individual numbers and replace them with their raw frequencies, so you can see exactly how a probability mathematician looks at the board. Look at the board now. These are no longer individual data points. These are frequencies. We have a frequency of 2 in A only, a frequency of 1 in the intersection, a frequency of 2 in B only, and a frequency of 1 outside of A and B. If we sum these frequencies up, so 2 plus 1 plus 2 plus 1, we get the total number of observations in our sample space, which is 6. Now let's look at how effortless it is to calculate our 3 core logical probabilities using nothing but these frequencies over our total count of 6. So first, let's find the probability of rolling a number that's even and prime. So that's the probability of A and B. To do this, we look directly at the frequency of our central overlap. The frequency is exactly 1 out of a total frequency of 6. Our probability is therefore a simple fraction, so the probability of A and B is equal to the fraction 1 over 6. Next, what's the probability of rolling an even number or a prime number? So that's the probability of A or B. Remember, the word or means you can be in circle A, circle B, or both. We therefore simply add up the frequencies trapped inside the two circles. So the frequency of 2 from A only, the frequency of 1 from the intersection, and the frequency of 2 from B only. This frequency of 5 out of our total frequency of 6 gives us the probability of A or B is equal to the fraction 5 over 6. Now let's look at the probability of finding not A. So rolling a number that is not even. To calculate this using frequencies, we completely block out circle A and add up every frequency remaining outside it. So in circle B, we have a frequency of 2, which is outside of circle A, and we have a frequency of 1, sitting out in the background rectangle. And so summing these gives us a total of 3, which we place over our total frequencies of 6, which gives us the fraction of 3 over 6. And simplifying this gives us the probability of not A equals the fraction 1 divided by 2, or a half. And so by shifting from listing elements to tracking strict frequencies, finding any probability on a Venn diagram becomes a mechanical process of adding up the counts in your target zones. But what happens if two events can never ever happen at the same time? So let's say when we roll a dice just once, event A is rolling a 4 and event B is rolling a 5. Can a single die roll show a number that is 4 and 5? No, it's physically impossible. In probability, we call these mutually exclusive events. Mutually exclusive means they exclude each other. If one happens, the other cannot. And so visually, their circles do not touch, and therefore there is no overlap. And so the frequency of outcomes in A and B is exactly 0. And so the probability of A and B is 0. Now let's translate these Venn diagrams into generic shading maps that work for any problem. The first is the probability of A and B. This represents the strict intersection. We shade only the middle overlap where both conditions are met simultaneously. Next is the probability of A or B. Remember, or is inclusive. It means you can be in A, you can be in B, or you can be in both. And so we shade everything inside both circles. And finally, we have the complement, the probability of not A. This means we want absolutely everything in our universe except circle A. And so we shade the outer background space and the exclusive right crescent of B. Instead of an abstract classroom problem, let's look at a real-world scenario from a dance club tracking a social group of 100 people and the 3 styles they dance, so foxtrot, jive and tango. We're given the following information with some unknowns, x and y, which we'd like to determine. To represent each type of dance, I've created 3 circles, F for foxtrot, J for jive, and T for tango on a Venn diagram. Our unknown variable x, shown here by the red shaded region on the Venn diagram, represents those people dancing tango and jive and foxtrot. Those dancing foxtrot and jive and not tango is also unknown and is represented by this red shaded region on the Venn diagram, where we'll place a y. Now let's populate the other regions of the Venn diagram with the information we're given. So the total dancing tango and not jive and not foxtrot is given as 24 and is represented by the red shaded region on the Venn diagram. And in this space, we'll put the number 24. Those dancing exclusively jive and therefore not tango and not foxtrot is given as 20 and is represented by the red shaded region on the Venn diagram. And in this space, we put the number 20. And those dancing exclusively foxtrot and therefore not tango and not jive is given as 12 and is represented by the red shaded region on the Venn diagram. And in this space, we put the number 12. And those dancing tango and jive, but not foxtrot, is given as 12 and is represented by the red shaded region on the Venn diagram. And in this space, we put the number 12. And those dancing tango and foxtrot, but not jive, is given as 8 and is represented by the red shaded region on the Venn diagram. And in this space, we place the number 8. And finally, we're given the number of people who don't perform any of the dances. So not tango and not jive and not foxtrot. And this is represented by the red shaded region on the Venn diagram. And we're told that this number is 11. We place 11 in this region. Now look at the red shaded region I've marked on the Venn diagram. This represents the total number of people that dance tango and jive. And the information we're given is that the total dancing tango and jive is equal to 17. Now in this number, we'll also get people that dance all three dances. So we'll also include people that dance the foxtrot. So we can now set up an equation using this information. And so from this information, we can determine that those people that perform all three dances, so X, as it's an unknown, plus those that perform tango and jive and not foxtrot, which we know is 12, is equal to a total of 17. So we can now solve this equation for X. And so X is equal to 5. And we can replace the X with a 5 on the Venn diagram. We're also told that those people dancing jive and foxtrot is equal to 13. And this is represented by the red region on the Venn diagram. And note that this also includes some people who dance all three. And so we can use this to create an equation where Y, so those people dancing foxtrot and jive, but not tango, plus those that dance all three dances, is equal to 13. And if we solve this equation, we get Y is equal to 8. And we can replace Y on the Venn diagram with the number 8. Now that we've populated all regions of the Venn diagram, we can now check this result. If we sum all these numbers, it should add up to the total group size of 100. And as you can see, when we do this, it does in fact add up to 100. We can now use these numbers to calculate some probabilities. So let's find the probability that a randomly selected person dances exactly 2 of the dances. And so on the Venn diagram, the numbers that represent those that dance exactly 2 dances are shown in the red shaded regions. We can now put these numbers over 100, as that's the total group size, and calculate this probability. And so plugging in these numbers, we have 12 plus 8 plus 8. And dividing this by the total group size, which is 100, gives a probability of 0.28, or a 28% chance that a randomly selected person from the group dances exactly 2 dances. Now let's find the probability that a randomly selected person from the group dances exactly all 3 of the dances. And so performing all 3 of the dances is represented by the red shaded region on the Venn diagram. And so we can take the number enclosed in this space, put it over 100, and find this probability. So we have 5 divided by 100, and this gives us 0.05. And so if we randomly select somebody from the group, the probability that they dance exactly all 3 dances is 0.05, or there's a 5% chance. In a recent video, we used algebra to find the exact count of every section of our Venn diagram. In this video, we're taking those numbers and turning them into probabilities. We're looking at all 8 regions of a Venn diagram related to students studying maths, biology, and chemistry. I'm going to show you that the addition rule and conditional probability aren't just scary formulas, they're just simple fractions based on the areas we've already labelled. At the end of the tutorial, you'll be able to look at any Venn diagram and see the probability instantly. So let's look at the addition rule. In probability, when you hear the word or, you should immediately think of a union. If I ask, what is the probability a student takes maths or biology? Many people make the mistake of just adding the total of the maths circle to the total of the biology circle. Let's look at why this fails on our diagram. If we have 28 students in the maths circle, so the green shaded region shown here, and 25 in the biology circle, so this green shaded region shown here, adding these numbers together gives us 53. But wait, our universal set is only 60. If we now add chemistry in there too, we'd be well over our total. So the secret is to look at this green shaded area here where maths and biology overlap. The area contains 2 of our 8 regions, maths and biology only, and the centre, which is all 3, and so includes chemistry. When you count the whole maths circle, you count those students, and when you count the whole biology circle, you count those same students again. And so to avoid double counting, we need to subtract the probability of those students doing maths and biology. And so the probability of those doing maths or biology is equal to the probability of those doing maths plus the probability of those doing biology minus the probability of those doing maths and biology. And that is the green shaded region you can see on the Venn diagram. And so to visualize this, make it clearer, let's look at the individual circles. In the maths circle, we have 3 and 7, which relates to those who do maths and biology. And similarly, we have it again in the biology circle, so 3 and 7. Now we don't want to double count these, so we need to subtract one occurrence of these, so 3 and 7, in order to get the correct total. So let's now look at the calculation for the probability of doing maths or biology. So looking at the numbers, the probability for doing maths or biology is the probability of doing maths, which is the total number doing maths, so that's 28, divided by 60. So why do we divide this number by 60? When we calculate the probability of a student doing maths or biology, we're asking, if I picked one student at random from this entire group of 60 people, what are the chances they'd be in those circles? If we only divided by the people inside the circles, we'd be ignoring the 5 students in our none group, but those 5 students are still part of the group. They are part of the total possible outcomes. So in probability, the denominator in this case is the universal set, which is 60. And we do the same for the probability of those students doing biology. So we take the total of 25 and divide it by 60. And similarly, the probability of those doing maths and biology, we sum the intersection area, so that's 3 plus 7 to give us 10, and we again divide by 60. And this gives us a total of 43 divided by 60, which in decimals is 0.72 corrected to 2 decimal places, and is the probability of students doing maths or biology. Now let's tackle conditional probability. This is written as the probability of one event happening, so in this case C, given another event M has already happened. The word given is your best friend in a Venn diagram. It tells you to throw away almost the entire diagram. So, for example, what is the probability that a student takes chemistry given that the same student is already in the maths group? The moment we hear given maths, the 60 students in the whole group don't matter anymore. The students who take only biology, only chemistry, or none are gone. Our universe has shrunk from 8 regions down to just the 4 regions inside the maths circle. So the green shaded region here. So let's look at the maths circle. We said it has 28 students. So 28 is the new total. The denominator of the fraction to calculate our probability is no longer 60 and is reduced to 28. Now remembering we want to find the probability of those students doing chemistry given that they're already doing maths. How many of those 28 students doing maths are also in the chemistry circle? So this green shaded region here. So this region has 2 sections to it. The maths and chemistry only, and the centre where students do maths, biology and chemistry. And those that do maths and chemistry only total 1, and those that do all 3 total 7. So this gives us a target of 8 students. So now let's look at the calculation for the probability that a student does chemistry given that they do maths. So to find this probability, we take the number of students that do chemistry and maths. So that's the sum of the green shaded region. So it's 1 plus 7, which gives 8, divided by the number of students that do maths, as this is a given. And we know this number is 28. And this gives us a value of 0.29 correct to 2 decimal places. So there's a 29% chance that a student does chemistry given that they do maths. Let's now take a look at some examples. So in our first example, let's calculate the probability that a student does chemistry or biology. If you'd like to play along, pause the video now. So the probability that a student studies chemistry or biology is the probability that they study chemistry, and that's the probability that they fall into this green shaded region here, plus the probability that they study biology, so the probability they fall into this region here, and minus the probability that they study both chemistry and biology. So that's the green shaded region here. And if we crunch the numbers, the probability that a student does chemistry is the total number of students that do chemistry, so that's 22, divided by the group total, which in this case is 60. The probability that a student does biology is the total number of students that do biology, which is 25, and again divided by the group total, which is 60, and minus the probability of those students that do chemistry and biology, which is 7 plus 2, which gives us 9. And this again we divide by the group total, which is 60. And this gives us a total of 38 divided by 60, which is 0.63 to 2 decimal places. So there's a 63% chance that a student will do chemistry or biology. Let's now look at this problem. What is the probability that a student studies maths given that the student studies biology? The word given changes our denominator. We are no longer thinking about the 60 students in the group. We are only looking at the 25 students in the biology circle. So this green shaded region here. Now, of the 25 students in the biology circle, how many of them are also in the maths circle? So this green shaded region here. So this is split into two areas, one which holds the maths and biology students only, and the central area which contains the maths, biology and chemistry students. So we need to sum these two areas to get the maths and biology students. And so to the calculation of the probability, we need the number of students that study maths and biology. So it's 7 and 3 added together, so that gives us 10, divided by the number of students in the biology circle. So that's the total number that do biology, and that equals 25. And this gives us a probability of 0.4. So there's a 40% chance that a student studies maths, given that they also study biology. Next, let's look at this problem. What's the probability of a student studying exactly 2 of the subjects? So to work this one out, we need to understand the regions. So exactly 2 means that they can be in the biology and chemistry only region, or they can be in the maths biology only region, or they can be in the maths and chemistry only region. If they're in any of the other regions, so the maths only region, the biology only region, or the chemistry only region, they'll only be doing one subject, exactly one subject. And if they're in the middle, they'll be doing 3 subjects. And so to find this probability, we sum the number in those regions. So in this case it's 3 plus 2 plus 1. And then we divide by the total of the group, which is again 60. And this gives us a total of 0.1. So in probability terms, there's a 10% chance that a student will study exactly 2 subjects. For our next example, let's see if we can find the probability that a student studies at most 1 subject. So this is a classic logic test. At most 1 means the student is in the 0 group or the exactly 1 group, and they haven't crossed the line into a second subject. So let's look at our regions. So the green shaded areas are the regions we need to look at when calculating this probability. So we need to look at the maths only region, the biology only region, the chemistry only region, and the region that contains none. And to find the probability, we need to sum the numbers in those regions and divide by a total of 60. So we have 17 plus 13 plus 12 plus 5 divided by 60. And this gives 47 divided by 60, which is equal to 0.78. And that's correct to 2 decimal places. So in probability terms, there's a 78% chance that a student studies at most 1 subject. And for this next one, Let's find the probability that a student does not study maths. And if you'd like to play along, pause the video now. Sometimes it's easier to count what we don't want. If we want the probability of not maths, we look at everything outside the maths circle. And so to calculate this probability, we're looking at the numbers in these green shaded regions. So none of these numbers touch the maths circle, so they are not maths. And therefore, to find the probability of a student not studying maths, we sum the numbers in these regions and divide by the total of 60. So we have 13 plus 2 plus 12 plus 5 divided by 60, and that gives us 32 divided by 60, which equals 0.53. So in probability terms, that means that there's a 53% chance that a student does not study maths. In basic probability, we ask questions like, what's the chance that it rains tomorrow? Or what's the chance that a student passes their exam? But in the real world, information changes. If I tell you that the sky is currently covered in heavy, dark storm clouds, your estimate of it raining tomorrow instantly shoots up. If I tell you a student stayed up until 4 a.m. playing video games the night before their test, your estimate of them passing drops. This is conditional probability. It's the probability of an event occurring given that another event has already happened. Mathematically, we write it like this. The probability of A given B, where A and B are separated by a bar. So this statement means the probability of A happening given that the event B has definitely occurred. So with conditional probability, new information shrinks your sample space. It restricts the total number of possibilities you're looking at. Let's take a look at a quick intuitive example. Let's suppose you roll a standard 6-sided die. The total sample space S is given by 1, 2, 3, 4, 5, and 6, as these are the possible outcomes. If I now ask, what's the probability of rolling a 4? Well, it's simply 1 chance in 6. So the probability is 1/6. But now let's apply a condition. What's the probability of rolling a 4 given that we're told that the die has landed on an even number? Because we're given this information and we know that the result is an even number, the odd numbers 1, 3, and 5 are instantly eliminated. The sample space has now shrunk. And so the new sample space is given by 2, 4, and 6, as there are now only 3 possibilities. And out of those 3 remaining possibilities, only one of them is a 4. And so the probability of rolling a 4, given that the die lands on an even number, is 1/3, as there's 1 chance in 3 of this outcome occurring. To handle more complex data, we need visual tools. Let's start with Venn diagrams. Venn diagrams are exceptional for static data groups, where items can belong to multiple categories at the same time. Let's look at the formula for conditional probability and relate it to a Venn diagram. So the probability of A given B is equal to the probability of A intersection B divided by the probability of B. So let's take a look at exactly why we divide by the probability of B. Remember, we have new information here, so we're given that B definitely happens. So this shrinks our sample space. This means that everything outside of circle B is now completely irrelevant. In a standard probability question, the denominator is the entire rectangular box shown here in green. And this is the total pool of possibilities. But because we know B happened, circle B becomes our entire new sample space. We divide by the probability of B because B is now the total probability left in our sample space. The numerator, the probability of A intersection B, is simply the slice of A that manages to live inside the new B territory. So we're calculating, out of the pool of B, how much of it belongs to A. Let's test this with a real example. Let's suppose a class of 30 students is surveyed about their streaming preferences. 18 students watch channel A, 10 students watch channel B, 4 students watch both, and 6 students watch neither. Let's now fill out our Venn diagram using this data. And so starting in the middle, we know that 4 students watch channel A and B. So those students that exclusively watch channel A is 18 minus 4. This leaves 14. And those students that exclusively watch channel B is 10 minus 4, which leaves 6. And those students that watch neither channel A or B is 6. And summing these numbers, so 14 plus 4 plus 6 plus 6, gives us a total number of 30 students. So now let's solve a conditional probability question. Let's find the probability that a randomly selected student watches channel B given that they watch channel A. So this is written, the probability of B given A. So A definitely happens. So our sample space has now shrunk and is shown by the green shaded region on the Venn diagram. And this represents the probability of A. So in our formula, the denominator is the probability of A, because we know A definitely happens. So the probability of A is 14 plus 4, so those numbers in the A circle, which total 18 students, divided by the total number of students, which is 30. And our numerator, the probability of A intersection B, and represented by the green shaded region on the Venn diagram, is given by the number of students that watch both channels, so that's 4, divided by the total number of students, which is 30. And so simplifying this, we get 4 divided by 18, which is equal to 2/9. So the probability that a randomly selected student watches channel B, given that they watch channel A, is 2/9. While Venn diagrams are perfect for stagnant groups, tree diagrams are the ultimate tool when events happen sequentially, or when one action directly influences the probability of the next action. Let's look at a weather and travel scenario to see how conditional probabilities are built directly into the structure of a tree. Suppose the probability that it rains tomorrow is 0.3, meaning the probability that it's fine is 0.7. If it rains, the probability you take the bus is 0.8, leaving a probability of 0.2 that you walk. If it's fine, the probability that you take the bus drops to 0.4, leaving a probability of 0.6 that you walk. The values on the second set of branches are already conditional probabilities. The probability of 0.8, shown here, isn't just the probability of taking the bus. It's the probability of taking the bus given that it rains. And the probability of 0.4, shown here, is explicitly the probability that you take the bus given that the weather is fine. So what now if we're asked to calculate the probability that it rains given we took the bus? We can calculate this using our formula. So it's the probability that it rains and the probability that we take the bus given it rains. And this is divided by the probability that we take the bus. So let's look at the numerator first. The probability that it rains and the probability that we take the bus given it rains is this branch of the tree diagram shown here. So this is the probability that it rains, 0.3, multiplied by the probability that we take the bus given it rains, and that's 0.8. And this is divided by the probability that we take the bus. And for the denominator, we need to calculate the probability that we take the bus. So looking at our tree diagram, the probability that we took the bus is governed by this branch here, which is the probability that we took the bus given that it rains, or this branch here, which is the probability that we took the bus given that the weather was fine. As it's one probability or another, we need to add the two probabilities. And so we have the probability that we take the bus given it rains is 0.3 multiplied by 0.8, and added to that the probability that we take the bus, given that the weather is fine, is 0.7 multiplied by 0.4. And if we perform the calculations on this, we get 0.24 divided by 0.52, which is equal to 0.46. So the probability that it rains, given that we take the bus, is 0.46. And this is correct to 2 decimal places. What is a probability tree diagram? At its core, a tree diagram is a visual map. We use it in probability when an experiment has multiple stages or sequence of steps, and we want to see every single possible outcome without guessing or missing anything. Think of it like a roadmap of choices. You start at a single point on the left side of your page. This is your starting node. Every time a coin is flipped, a card is drawn, or a match is played, the path splits. We call these paths branches. By the time you travel all the way to the far right side of the page, the tips of those final branches display every single unique outcome that could possibly happen. We rely on these diagrams for 2 major reasons. The first is it prevents mistakes. It acts as a visual checklist, so you never accidentally overlook a combination in a complex problem. And 2, it organizes the mathematics. By writing the probability of each outcome directly onto its corresponding branch, the diagram explicitly lays out which fraction or decimals you need to calculate. Let's look at how events chain together so we can see exactly how these diagrams are built. In probability, we frequently deal with different classifications of events. Let's define them by relating them directly to the structure of a tree diagram using a simple 2-stage experiment. Rolling a die to try and get a 6, and then flipping a coin. First, we have an individual event. This is a single action with its own distinct set of outcomes, completely isolated from anything else. On the tree, this is represented by a single splitting point or node, with branches shooting out from it. For example, stage 1 is your die roll. Landing on a 6 is an individual outcome. Because there is only one 6 on a 6-sided die, that specific branch gets a probability label of 1/6, leaving a 5/6 probability for not rolling a 6. Now look closely at that initial splitting node, so here and here. Because the 2 branches represent every single possible thing that can occur during that action, the probabilities on any single set of branches must always sum to 1. So in this case, we have a probability of 1/6 plus a probability of 5/6, and this sums to 1. And therefore, if you know the probability of one branch, you can automatically find its pair by subtracting from 1. So therefore, our top branch has a probability of 1/6. So our bottom branch must have a probability of 1 minus 1/6, which equals 5/6. Next, we have a successive event. This means one event happens directly after another in a sequence. So on the tree, this is represented by branches growing out of previous branches as you move from left to right. So for example, after rolling the die, you flip a coin. So this second stage consists of a new set of heads and tails branches growing directly out of the tips of stage 1 branches. Landing on a heads on this coin flip is an individual probability of a half, and landing on a tails also has a probability of a half. And notice once again that the probabilities on each branch, in this case a half plus a half, sums to 1. Now when we look at the final results of these stages tracked together, we get a combined event. So on the tree, this represents the entire journey from the starting route to the final branch tip. So for example, rolling a 6 on the die and landing a heads on the coin flip. To extract these combined events from the diagram, we must master 2 foundational language statements, and or. Here's how you read those numerical values directly off the tree structure. The word "and" means that we require a specific sequence of events to happen, one after the other. For example, rolling a 6 and then flipping ahead. On the tree diagram, we obtain this by following a single continuous pathway from left to right. And because we need both to happen along that timeline, we multiply the probabilities along that specific route. So we have 1/6, which is the probability of rolling a 6 on a die, multiplied by a half, the probability of flipping ahead. And this gives us a probability of 1/12. Now let's look at probabilities that include the OR statement. OR means you are satisfied with multiple different final scenarios. For example, you want to know the total probability of success in a game where you win if you roll a 6 and flip ahead, which is the probability of rolling a 6, so 1/6, multiplied by the probability of flipping ahead, which is a half, and this equals 1/12, or the probability of not rolling a 6 and flipping ahead. So this branch here, which is the probability of not rolling a 6, so 5/6, multiplied by the probability of flipping ahead, which is a half, and this equals 5/12. On the tree diagram, we obtain this final probability by looking down the very far right column of the endpoints. We locate the completely separate branch tips that fit the criteria. We then calculate the individual probabilities of each of the path values and add these probabilities together. So in our example, the probability of rolling a 6 and flipping ahead, so this branch here, gives us a probability of a 12th, or the probability of not rolling a 6 and flipping ahead, so this branch here, gives us a probability of 5/12. And so the probability of one or the other is 1/12 plus 5/12, which is 6/12, and this simplifies to a half. To make absolutely sure the diagram layout is correct, let's calculate the remaining paths to find the probability of each of the branches. So the probability of rolling a 6 and flipping ahead is 1/6 multiplied by a half, which is 1/12. The probability of rolling a 6 and flipping a tail is 1/6 multiplied by half, which is 1/12. The probability of rolling something other than a 6 and flipping a heads is 5/6 multiplied by half, which is 5/12. And the probability of rolling something other than a 6 and flipping a tail is 5/6 multiplied by a half, which is 5/12. And now the rule for any tree diagram is that if we sum down the entire right-hand side of the column to find the final probability outcomes, the sum of these must be 1. So we can verify this on our diagram. So we have 1/12 plus 1/12 plus 5/12 plus 5/12, and this equals 1. If the right-hand side total does not equal 1, you know instantly that you've made a manual error or missed a path entirely. Now let's apply what we've just learned to this daily scenario. Suppose the probability that it rains tomorrow is 0.3, meaning the probability that it's fine is 0.7. If it rains, the probability that you take the bus to school is 0.8, meaning the probability of walking is 0.2. And if the weather's fine, the probability that you take the bus is 0.4, leaving a 0.6 probability of walking. Let's find the probability of it raining tomorrow and you take the bus to school. So in the tree diagram, we're looking at this path. Now, because it's an AND condition, we multiply the probabilities along the branches. So the probability that it rains is 0.3, and the probability we take the bus, which is 0.8. And this gives us a probability of 0.24. Now, what if the question asks, what is the total probability that you take the bus tomorrow, regardless of what the weather does? So this is an OR condition, because you successfully achieve your goal if it rains and you take the bus, or if it's fine and you take the bus. So first, we calculate that second distinct pathway, so the weather's fine and we take the bus. So this branch here. So this gives the probability of it being fine, so 0.7, and the probability of us taking the bus, which is 0.4. And this gives a probability of 0.28. And because we can achieve the desired result using the top or the bottom path, we take the final column outcomes and add them together. So we have 0.24 plus 0.28, and this gives us a probability of 0.52. And so there's a 52% chance overall that we'll end up taking the bus. Let's now reinforce the structural checks we learned earlier to double check our manual arithmetic. So for each of the individual branches, the probabilities must add up to 1. So the probability of the weather being rainy is 0.3, and the probability of the weather being fine is 0.7. We have 0.3 plus 0.7, and this correctly adds up to 1. And whether we take the bus or we walk is determined by two branches. So in the top branch, the probability of taking the bus is 0.8, and the probability of walking is 0.2. And 0.8 plus 0.2 is equal to 1. And then in the bottom branch, we have the probability of taking the bus is 0.4, and the probability of walking is 0.6. So we have 0.4 plus 0.6, and this is also equal to 1. So the last check we need to do is to determine that the sum of all final outcomes for those probabilities down the right-hand side equals 1. Now to do this, I've filled in the remaining pathways. So let's do a check. So 0.24 plus 0.06 plus 0.28 plus 0.42, all these add up to 1. Sometimes calculating a large number of paths is highly inefficient, and in some circumstances we can use the complement rule as a shortcut. Suppose we're asked for the probability that we do not experience the combination of the weather being fine and walking. Instead of adding up the other three matching paths, we can target the single outcome we don't want. So the probability that the weather is fine and we walk takes us down this branch here. And the probability of this happening is 0.42. And so the probability of this not happening is equal to 1 minus 0.42, which equals 0.58. Let's now look at what happens if we have an experiment with 3 or more outcomes. Imagine a chess player entering a 2-game tournament. For any single match they play, there are 3 distinct possibilities. The probability they win is a half. The probability they lose is a third. And the probability that they draw is 1/6. And so for match 1, we have 3 branches: a win, a lose, and a draw. Then the end of each of these branches splits into 3 more sub-branches for match 2. And this generates 9 final combinations in total. So let's answer a specific question. What is the probability that the player wins exactly one match and draws the other? To find this combined event, we look at our tree diagram and we find the paths that meet this criteria. And so there are 2 paths. If in the first match the player wins, then in the second match, the player must draw. So it follows this path. And if in the first match the player draws, then in the second match the player must win. And so it follows this path. And so the probability that the player wins the first match and draws the second match is 1/2 multiplied by 1/6, which equals 1/12. And the probability that the player draws the first match and then goes on to win the second match is 1/6 multiplied by 1/2, which is also equal to 1/12. Now we can use our OR rule. Because the player can achieve this outcome via path 1 or path 2, we add the final probabilities together. So we have 1/12 plus 1/12, which equals 2/12, and this simplifies to 1/6. And so the probability of the player finishing the tournament with exactly one win and one draw is 1/6. Let's now take a look at this problem. Let's suppose we have a bag which contains 4 red sweets and 6 green sweets. A child comes along and selects a sweet at random from the bag and eats it. They then select a second sweet at random from the bag. Let's see if we can draw a fully labeled tree diagram to show all possible outcomes and probabilities. And then let's see if we can find the probability that the child chooses 2 sweets of the same color. And finally, let's calculate the probability that the child selects at least one red sweet. So this is our tree diagram. So we have a bag of sweets with 6 green sweets and 4 red sweets. So in the first instance, the child can choose a sweet, and the sweet color might be red or green. Now, as there are 10 sweets in total and 4 of them are red, the probability that the child chooses a red sweet is 4 divided by 10, and this equals 2/5. And the probability that a child chooses a green sweet when there are 6 green sweets is 6 divided by 10, which equals 3/5. And what happens next is very important. The child chooses a sweet and then eats it. So therefore, this is a dependent event without replacement. And so the fractions must change for stage 2. So if the child chooses a red sweet and eats it, there are now only 3 red sweets available and only 9 sweets in total. If the child chooses a green sweet, there will then only be 5 green sweets available out of a total of 9. So if in the first instance the child chooses a red sweet, the new probability of choosing a red sweet, so this branch here, is 3 divided by 9, where 3 are the remaining red sweets and 9 is the total number of sweets, and this equals 1/3. If in the first instance the child chooses a red sweet and then goes on to choose a green sweet, so this path here, there remains a total of 6 green sweets in the bag out of a total of 9. So the probability of this happening is 6 divided by 9, which equals 2/3. If in the first stage the child chooses a green sweet and then goes on to choose a red sweet, so this path here, in the second selection, 4 red sweets remain out of a total of 9. So the probability is 4 divided by 9. If, however, in the first instance, the child chooses a green sweet and then goes on to choose another green sweet, so this path here, in the second selection, there are only 5 green sweets in the bag out of a total of 9. And so the probability of this happening is 5 divided by 9. Let's now calculate the probability that a child chooses 2 sweets of the same color. There are 2 possibilities here. The child could choose 2 red sweets, which would be this path here, or 2 green sweets, so this path here. In the first path, the probability of choosing 2 red sweets, so a red and a red, would be 1/3 multiplied by 2/5, and this would equal 2/15. And the probability of selecting 2 green sweets would be 3/5 multiplied by 5/9, which would be 15 divided by 45, or 1/3. Now the probability of choosing 2 reds or 2 green sweets would be these probabilities added together. So we have 2/15 plus 1/3, which equals 7/15. And now for the final part, we want to calculate the probability that the child selects at least one red sweet. So let's look at the potential paths on the tree diagram. So in stage 1, the child can choose a red sweet for this path here, and then go on to choose another red sweet, this path here, or a green sweet, this path here. Both would satisfy the criteria of choosing at least one red sweet. If in the first scenario, the child chooses a green sweet first, so this path here, then to satisfy the criteria, the next selection must be red, so this path here. So we have 3 possibilities: path 1, path 2, or path 3. In the first path, the probability of this happening is 1/3 multiplied by 2/5, which equals 2/15. In the second path, the probability of this happening is 2/5 multiplied by 2/3, which is 4/15. And in the third path, the probability of this happening is 3/5 multiplied by 4/9, which equals 12/45. And as either of these paths will satisfy the criteria, we have two OR operations, the path 1 or path 2 or path 3. And so we need to sum the probabilities. So we have 2/15 plus 4/15 plus 12/45, and this gives us a probability of 2/3. So the probability that the child chooses at least one red sweet is 2/3. If I flip a coin and get heads 5 times in a row, what's the chance I get heads on the 6th flip? Well, the answer is still 50%. The coin has no memory. This is the core idea behind this video: dependent and independent events, and how we identify each. In statistics, whether two events are dependent or independent changes how we calculate probability. Get this wrong and your answer will be way off. Let's break this down and first understand what an independent event is. Two events are independent if the outcome of one does not affect the outcome of the other, and where the probability of A and B is equal to the probability of A multiplied by the probability of B. Let's say we have two events. Event A is flipping a coin, and event B is rolling a die. When we flip the coin, the probability of a heads is a half, as there's one chance in two. And when we roll the die, the probability of rolling a 4 is 1/6, as there's one chance in 6 of rolling a 4. And so the probability of flipping a head and rolling a 4 is a half multiplied by a 1/6, which equals 1/12. And so these events are independent, as the outcome of event A does not affect the probability of event B. Let's take a look at another example. Let's suppose we roll a die twice and calculate the probability of rolling a 6 on both occasions. So on the first roll, the probability of rolling a 6 is one chance in 6, so 1/6. And on the second roll, the probability of rolling a 6 is also one chance in 6, so 1/6. So the probability of rolling a 6 on the first roll and a 6 on the second roll is 1/6 multiplied by 1/6, and this equals 1/36. So these events are independent, as the outcome of the first event does not affect the probability of the second event. In each case, the chances of rolling a 6 are the same. So what are the key phrases we need to look for when looking for independent events? Well, one is with replacement, and another would be separate events. These usually signal independence. Now let's take a look at dependent events. Two events are said to be dependent if the outcome of the first does affect the probability of the second. And so for two events, A and B, the probability of A and B is equal to the probability of A multiplied by the probability of B given A. Let's take a look at an example of this. Let's suppose a deck of cards has 52 cards, and in the deck we have 4 aces. Let's suppose we draw one card and don't put it back, and then we draw another. So what's the probability of drawing 2 successive aces from our 52 card deck? So when we draw our first card, what's the probability that it's going to be an ace? Well, we know there are 52 cards in the deck, and we know that there are 4 aces. So there are 4 chances in 52. So the probability is 4 divided by 52. Now, when we draw the second card, we want to calculate the probability of it being an ace, given that the first card we drew was an ace. Now remember, we didn't replace the first card, so there are now only 51 cards in the deck. And given that the first card was an ace, there are now only 3 aces in the deck. So when we draw the second card, there are 3 chances in 51 that the card will be an ace. So the probability of drawing 2 aces is 4 over 52 multiplied by 3 over 51, and this gives us 1 divided by 221. So these are dependent events, as the outcome of the first event affects the probability of the second. Let's take a look at another example of this. Let's imagine we have a bag with 10 marbles in. 5 of the marbles are blue and 5 of the marbles are red. If we pull one marble out of the bag and don't replace it, and then we pull another marble out of the bag, what's the probability that both marbles are red? So let's see how we calculate this. When we pull the first marble out of the bag, there are 10 marbles in the bag, and we know that 5 are red. So there's 5 chances in 10 of pulling a red marble out of the bag. Now we don't replace this marble, but we pull another marble out of the bag. And the probability of it also being red, given that the first marble was red, is 4 over 9, because there are now only 9 marbles in the bag, and we know only 4 of them are red. So the probability of both marbles being red is equal to 5 over 10 multiplied by 4 over 9, which is 20 over 90, which is 2/9. So these events are dependent, as the outcome of the first event does affect the probability of the second event. So the key phrases to look for when trying to determine whether events are dependent would be without replacement or given that. These usually signal dependence. So here's a flowchart to help us distinguish between dependent and independent events. So we can ask ourselves the question, does removing or using up the first outcome change what's left? If this is a yes, then the events are likely to be dependent. We could ask, could you repeat the first event infinitely without changing the setup? If this is a yes, then the events are likely to be independent. And we could ask, does knowing what happened in the first event tell me anything new about the second? If this is a yes, then the events are likely to be dependent. If this is a no, the events are likely to be independent. Let's take a look at these real-world events and see if we can decide whether they're dependent or independent events. So in the first, we have event A, which is the weather today, and event B, which is the weather tomorrow. Are these events dependent or independent? If you'd like to play along, pause the video now. So these events are dependent because today's weather influences tomorrow's likelihood. So for the second one, event A is winning the lottery this week, and event B is winning it again next week with a new ticket. If you'd like to play along, pause the video now. So these events are independent, as each lottery draw is separate. And for 3, event A is picking a name out of a hat for a raffle, and then event B is picking a second name without putting the first name back. Are these events dependent or independent? If you'd like to play along, pause the video now. So these events are dependent because we've taken the first name out of the hat without replacement, and therefore this influences the probability of the second event. And for our fourth example, event A is whether it rains in Tokyo, and event B, whether you flip a heads on a coin in New York. If you'd like to play along, pause the video now. So these events are independent, as they are completely unrelated systems. So the probability of one does not affect the probability of another. So let's summarize what we've just learned. So in terms of definition, events are independent if one event doesn't affect the other. They are dependent if one event changes the odds of the other. When we look at the formula, for independent events, the formula is the probability of A multiplied by the probability of B. And for dependent events, the formula is the probability of A multiplied by the probability of B given A. And we can use clue words to determine whether events are dependent or independent. So for independent events, the clue words would be with replacement and separately. For dependent events, the clue words would be without replacement and given that. An example of independent events would be a coin flip and a die roll. And an example of dependent events would be drawing cards without replacement. Let's say you take a test for a rare disease. The test is 99% accurate and it comes back positive. What's the probability you actually have the disease? Most people say 99%. The real answer might shock you. It could be as low as 2%. By the end of this video, you'll know exactly why, and you'll never look at probability the same way again. Let's talk about Bayes' theorem. Bayes' theorem is one of the most useful ideas in all of probability. It's used in spam filters, medical diagnosis, courtroom evidence, AI, even search and rescue operations. At its heart, it answers one question. When new evidence comes in, how should you update what you believe? That's it. That's the whole idea. Let's build it up from scratch. Before we get to the formula, we need two ideas you probably already know. First, conditional probability. We write the probability of A given B as the probability of AB with a vertical bar in between. It means the probability of A happening given that B definitely happened. Next, we have the multiplication rule, where the probability of A and B is equal to the probability of A multiplied by the probability of B given A. That's just saying the chance of two things both happening equals the chance of the first multiplied by the chance of the second, given that the first definitely happened. Now here's the key insight Bayes had. You can write the probability of A and B in two ways. We've seen one, the probability of A and the probability of B, but you can also write it as the probability of B and A, which equates to the probability of B multiplied by the probability of A given B. And so this gives us the probability of A multiplied by the probability of B given A is equal to the probability of B multiplied by the probability of A given B, as both sides of this equation are equivalent to the probability of A intersection B. And rearranging this equation, we get Bayes' theorem, where the probability of A given B is equal to the probability of A multiplied by the probability of B given A divided by the probability of B. Now if we look at the constituent parts of this formula, the probability of A is known as the prior probability, and it's what you believe before seeing any evidence. The probability of B given A is known as the likelihood, as it's the probability of B happening given that A definitely happened. The probability of B is known as the evidence, and it's the overall probability of seeing that evidence at all under every possible scenario. And the probability of A given B is known as the posterior probability, and it's the probability of A happening given that B has definitely happened. So let's put Bayes' theorem to use with some examples. So let's go back to our opening question where we asked, what's the probability of having a disease given that we tested positive for it? And set some real numbers. So let's say 1 in 1,000 people actually have the disease. So the probability of having the disease is 0.001. And the test correctly identifies the disease 99% of the time. So the probability of having a positive test, given that you have the disease, is 0.99. And let's say there's a false positive rate of 5%. So 5% of healthy people test positive. So the probability of testing positive, given that you don't have the disease, is 0.05. So let's draw this as a tree diagram. So the first two branches of the tree diagram show the probability of having the disease and not having the disease. Now we're told that the probability of having the disease is 0.001. So the probability of not having the disease is 0.999. And we're also told that the test correctly identifies the disease 99% of the time. So the probability of testing positive, given that we have the disease, is 0.99. So this branch here. And we're also told that there's a false positive rate of 5%. So 5% of people test positive even though they do not have the disease. And so the probability of testing positive, given that the person is healthy, so without the disease, is 0.05. So this branch on the tree diagram. And looking at the other branches of the tree diagram, the probability of having the disease and testing negative, so this branch here, is 0.01. And the probability of not having the disease and testing negative, so this branch here, is 0.95. As these values are the complements of testing positive. So if you remember, we subtract 0.99 from 1, and that gives us 0.01. And we subtract 0.05 from 1, and that gives 0.95. And now if we apply Bayes' theorem, the probability of having the disease, given that we've tested positive, is the probability of having the disease multiplied by the probability of testing positive, given that we have the disease, divided by the probability of testing positive. And so the probability of having the disease we know is 0.001. And the probability of testing positive, given that we have the disease, so this branch here on the tree diagram, is 0.99. Now the probability of testing positive can come from two paths on the tree diagram. So this path, or this path. So it's an OR, so we need to add those two probabilities together. And the first probability is 0.001 multiplied by 0.99. So this number here multiplied by this number here. And the second probability is 0.999 multiplied by 0.05. So this number here multiplied by this number here. And if we multiply these numbers out, in the numerator we have 0.00099 divided by the denominator, which is 0.05094, and this gives 0.0194, so a bit less than 2%. So as we can see, given the extra information, the probability of having the disease, given that we've tested positive, is less than 2%. And this is because the disease is so rare, so 1 in 1,000, that the pool of healthy people testing false positive, so 5% of 999 people, vastly outnumbers the truly sick people testing correctly positive. So that's 99% of one person. Let's look at another example, because this is where Bayes' theorem really earns its keep, reversing a tree diagram. So let's say we have two factories supplying a warehouse. Factory A supplies 60% of items, Factory B supplies 40%. Factory B has a 5% defect rate. Factory A has a 3% defect rate. You pick an item at random and it's defective. What's the probability it came from Factory B? Let's take a look at the tree diagram for this. So Factory A supplies 60% of items and Factory B supplies 40%. So the probability an item came from Factory A is 0.6 and the probability it came from Factory B is 0.4. Now, if an item came from Factory A, the probability it's defective is 0.03 or 3%, and therefore the probability it's not defective is 0.97, and this is 1 minus 0.03. And if an item comes from Factory B, the probability it's defective is 0.05 or 5%. And therefore, the probability it's not defective is 0.95, as that's 1 minus 0.05. So we want to find the probability an item came from Factory B, given that it's defective. So let's use Bayes' theorem. So the probability it's from Factory B, given that it's defective, is the probability it's from Factory B multiplied by the probability it's defective, given that it's from Factory B, divided by the probability it's defective. And so the probability that the item is from Factory B is given by this branch of the tree diagram. So it's a 0.4. And the probability it's defective, given it's from Factory B, is given by this branch on the tree diagram. So it's 0.05. Now the probability an item is defective is given by two paths. So the probability it's defective and from factory A, so this path, or the probability it's defective and from factory B, so this path. And as it's an either or, we need to add the probabilities together. So the first probability is 0.6 multiplied by 0.03, so these numbers here. And the second is 0.4 multiplied by 0.05, so these numbers here. And when we simplify this, we get 0.2 divided by 0.38, which gives us a probability of 0.53 correct to 2 decimal places. So the probability that a randomly selected item came from factory B, given that it's defective, is 0.53. So over half the defective items, about 53%, come from factory B, even though factory B only makes 40% of all items. So the higher the defective rate shifts the odds. In this video, we're going to look at a series of exam-style probability questions, and I'll show you the exact step-by-step methods to solve these. So let's start with the first one. In a group of 60 students, 28 study French, 25 study Spanish, and 10 study both. In part A, we're asked to draw a Venn diagram to represent this information. In part B, we're asked to find the probability of the union between those studying French and those studying Spanish. And then in part C, we're asked to find the probability of the intersection of those studying French and those not studying Spanish. And for part D, a student is chosen at random from those that study French, and we're asked to find the probability that they also study Spanish. If you'd like to play along, pause the video now. So our Venn diagram contains two intersecting circles drawn within a rectangle. One circle is marked F for French, and the other circle is marked S for Spanish. So let's start plugging the numbers into the Venn diagram. So we'll begin with those that study both French and Spanish, so the intersection of the Venn diagram. And we're told that 10 students study both. So we'll place the number 10 in this area. And then we're told that 28 students study French. Now we've already got 10 in the intersection, so we need to subtract 10 from 28. And this gives us 18. And these 18 represent those students that exclusively study French. Next, we're told that 25 students study Spanish. Now we already know that 10 students study French and Spanish, so we need to subtract the number 10 from 25, and this gives us 15. So we place the number 15 in this area of the Venn diagram, and this represents those students that exclusively study Spanish. And finally, if we add up the numbers 18, 10, and 15, we get 43. And if we subtract this from the total number of students in the group, which is 60, we get 17. And this represents the number of students who study neither French nor Spanish. And this number is placed outside the two circles, but within the rectangle. And for part B, we need to find the probability that a randomly selected student studies either French or Spanish or both, which means the probability of the union of those studying French and Spanish, which is represented by the green shaded region on the Venn diagram. So if we sum these numbers, we have 18 plus 10 plus 15 and divide by 60, so the total sample space, we get a probability of 43 divided by 60. In part C, we want to find the probability of F intersection S prime, which is the probability that a randomly selected student studies French and not Spanish. And so we're looking for the common part of these two groups. So those that study French is represented by the green shaded region on the Venn diagram. And those in the not Spanish group are represented by the green shaded region on the Venn diagram. So the common point, or the intersection of these two groups, is shown by the green shaded region here on the Venn diagram. And that group has 18 students. So our probability is 18 divided by the total sample space, which is 60, and this gives us a probability of 3/10. In part D, we're told that a student is randomly selected from the group that study French, and we want to find the probability that they also study Spanish. So decoding this is the probability that a student studies Spanish given that they definitely study French. So this is conditional probability, and we have a formula for this. It's the probability that a student studies French and Spanish divided by the probability that the student studies French. So on our Venn diagram, the probability that a student studies French and Spanish, so the intersection of French and Spanish, is shown by the green shaded region. So we see that there are 10 students that study French and Spanish. So if we divide 10 by our sample space of 60, we get this probability. And the probability that a student studies French is shown by the green shaded region on the Venn diagram. So in this region, we have two numbers, 18 and 10. So if we sum these, we get 28, and divide this by the total in our sample space, which is 60, we get a probability of 28 over 60. And simplifying this, we get 5 divided by 14. And this is the probability that a student studies Spanish given that they study French. In our next question, we're told that a fair coin is tossed and a fair die is rolled. The first part of the question, part A, asks us to find the probability of getting a head and a number greater than 4. And part B asks us to find the probability of getting a head or a number greater than 4, or both. If you'd like to play along, pause the video now. And so for part A, the probability that when we flip a coin, we get a head is 1 chance in 2. This probability is 1/2. And to find the probability of rolling a die and getting a number greater than 4, we have to look at the various outcomes. So when we roll a die, we can get an outcome of 1 to 6. So the only numbers greater than 4 will be 5 and 6. So there are 2 chances in 6 of rolling a number greater than 4. And those numbers are 5 and 6. So the probability of rolling a number greater than 4 is equal to 1/3. And for this question, it's important to understand that rolling a die and flipping a coin are independent events. The one event does not affect the other. So the probability of flipping a head and, when we roll a die, getting a number greater than 4 is the probability of flipping a head multiplied by the probability of rolling a number greater than 4. So we know that the probability of flipping a head is 1/2, and we know that the probability of getting a number greater than 4 when we roll a die is 1/3. So our total probability is 1/2 multiplied by 1/3, and this gives us a probability of 1/6. And for part B, we're asked to find the probability of getting a head or a number greater than 4, or both. If we translate this is asking us to find the probability of getting a head unioned with rolling a number greater than 4 on the die. And for this, we can use the addition rule. And we have a formula for this. It's the probability of getting a head plus the probability of rolling a number greater than 4 minus the probability of getting a head and rolling a number greater than 4. And we subtract this probability to avoid double counting. Let's quickly look at why we make this subtraction using a Venn diagram. So we have 2 circles, flipping a head and rolling a number greater than 4. And so flipping a head is represented by the green shaded region on the Venn diagram. And rolling a number greater than 4 is represented by this green shaded region on the Venn diagram. Note that the intersection of the two, represented by this green shaded region, appeared in both scenarios. And so we have to subtract one of them to avoid double counting. So to calculate the probability, we need the probability of a head plus the probability of rolling a number greater than 4 minus the probability of flipping a head and rolling a number greater than 4. And we know these probabilities from part A. So the probability of flipping a head is 1/2 plus probability of rolling a number greater than 4 is a third, minus the probability of flipping ahead and rolling a number greater than 4 is 1/6. And this gives us a total probability of 2/3. So the probability of getting ahead or a number greater than 4 or both is 2/3. And we can verify this probability by looking at all the different possible outcomes. When we flip a coin and we roll a die, the different outcomes would be flipping ahead and rolling 1 to 6 on the die, or flipping a tail and rolling 1 to 6 on a die. So that's a total of 12 possible outcomes. And if we look at the outcomes that satisfy this probability, we have flipping ahead and rolling 1 through 6 on the die, and flipping a tail and rolling 5 or 6 on the die. So there are 8 possible outcomes that satisfy this. And so we have 8 chances in 12, which gives us a probability of 2/3. And for our third question, we're told that a bag contains 5 red counters and 3 blue counters. 2 counters are drawn at random, one after another, without replacement. And part A asks us to draw a tree diagram to show all possible outcomes with probabilities on each branch. Part B asks us to find the probability that both counters are red, and part C asks us to find the probability that the 2 counters are different colours. So let's start with our tree diagram. There are 8 counters in the bag, and we know that 5 are red. So the probability of selecting a red counter at random is 5/8. And 3 of the counters are blue, so the probability of selecting a blue counter at random is 3/8. Now here's the important part. Once we've taken the first counter out, we don't replace it. So now there's only 7 counters in the bag. And if the first counter was red, there are only 4 red counters in the bag. So the chances of selecting a red counter a second time is 4/7. And the chance of selecting a blue counter, if the first counter was red, is 3/7, as there are still 3 counters in the bag. And if the first counter was blue, the chance of selecting a red counter would be 5/7, as there are still 5 red counters in the bag. And the chances of it being blue would be 2/7, as there are now only 2 blue counters in the bag. And so for part B, the probability that both counters coming out of the bag are red would be this probability multiplied by this probability. And this gives us a total probability of 5/8 multiplied by 4/7, which is equal to 20 divided by 56, which further simplifies to 5 divided by 14. And for part C, we want to find the probability that the 2 counters are different colours. So we could have the scenario where the first counter drawn is red, so this branch here, and the second counter drawn out is blue, so this branch here. Or we could have the scenario where the first counter drawn is blue, this branch here, and then the second counter is red, so this branch here. So we have the probability that the first counter is blue and the second counter is red, or, so we add the probabilities, the probability that the first counter is red and the second is blue. So now we can pick these probabilities off the tree diagram. So the probability of blue followed by red is 3/8 multiplied by 5/7. So 3/8 multiplied by 5/7 plus the probability of blue following red is 5/8 and 3/7. So 5/8 multiplied by 3/7, and this gives 15/56 plus 15/56, which gives a total probability of 15/28. For question 4, we're given a survey of 100 people, and it recorded whether they owned a car and whether they owned a bike, and the data is shown in the table. Part A of the question asks us to find the probability that a randomly selected person owns a bike. Part B asks us to find the probability that a randomly selected person owns a bike, given that they own a car. And part C asks us to determine, showing our workings, whether owning a car and owning a bicycle are independent. So let's start by plotting this information on a Venn diagram. It's a two-circle Venn diagram. One circle represents the car owners, and the other circle represents the bicycle owners. Outside of the circle and within the rectangle represents those people that don't own a car or a bike. So let's start filling in the numbers. So from the table, those that own a car and a bicycle total 18. And this is the green shaded region on the Venn diagram. So I've placed the number 18 in this region. And those people that own a car but no bike totals 42 and is represented by the green shaded region on the Venn diagram. So this means they're exclusively car owners. So I've placed the number 42 in this region. And we can also see from the table of data that those people owning a bike but not a car is equal to 27. And this is represented by the green shaded region. So these are exclusively bike owners. And I've placed the number 27 here. So part A asks us to find the probability of owning a bicycle. So for this, we can sum the numbers that represent bike owners. So in this case, 27 and 18. So we add these together and we divide by the total in the sample space, which is 100. And this gives us a probability of 0.45. And for part B, we're asked to find the probability of a randomly selected person owning a bicycle given that they own a car. So they definitely own a car. And we have a formula for this. So it's the probability of the intersection between bike and car divided by the probability of owning a car. So this is conditional probability, where our sample space shrinks because we definitely know that they're car owners. So the probability of owning a car and a bicycle is the intersection of the two. So it's this number here divided by the total in the sample space. So we have 18 divided by 100. And we need to divide this by the probability of owning a car. So the total number owning a car is 42 plus 18, which comes to 60. And we need to divide this by the total in the sample space, which is 100. And this gives us a total probability of 3/10 or 0.3. And in part C of the question, we're asked to determine, showing our workings, whether owning a car and owning a bicycle are independent. Well, if these two events were independent, then the probability of owning a bicycle, given that we already own a car, would equal the probability that we own a bicycle. And we've worked out the probability of owning a bicycle, given that we already own a car, which is 0.3. And we've calculated the probability of owning a bicycle, which is 0.45. And as we can see, these numbers are different, and therefore the events are not independent. We're going to look at a series of exam-style probability questions, and I'll show you the exact step-by-step methods to solve them. In the first question, we're told that events A and B are such that the probability of A is 0.4, the probability of B is 0.35, and the probability of A intersection B is 0.14. Part A of the question asks us to show that A and B are independent. Part B asks us to state with reason whether A and B are mutually exclusive. And Part C asks us to find the probability of A union B. If you'd like to play along, pause the video now. In Part A, we need to show that events A and B are independent. Now, for the events to be independent, the probability of one event happening, given that the other has definitely happened, so let's say the probability of A given B is equal to the probability of A. So what this means is that if two events are independent, knowing that event B happened gives you zero new information about event A. So the probability of A remains completely unchanged. So event B is entirely irrelevant to the outcome of A. So let's calculate the probability of A given B and see if it equals the probability of A. So for the probability of A given B, we have a formula. It's the probability of A intersection B divided by the probability of B. Now we're given the probability of A intersection B as 0.14, and we're given the probability of B, which is 0.35. And dividing 0.14 by 0.35 gives 0.4. which is the probability of A that we're given in the question. So in this case, the probability of A given B is equal to the probability of A, and therefore the events are independent. Now for part B of the question, we're asked to state with reason whether A and B are mutually exclusive. So what does mutually exclusive actually mean? Well, it means the probability of them overlapping or happening at the exact same time is absolutely zero. So if we drew two mutually exclusive events on a Venn diagram, we'd have two circles which did not overlap. And so if event A and B were mutually exclusive, the probability of A intersection B would equal 0. Now in the question, we're told that the probability of A intersection B is equal to 0.14. Now this is not equal to 0, and therefore the two events are not mutually exclusive. And for part C of the question, we're asked to find the probability of A union B. And to find this probability, we can use the addition rule. And we have a formula for this. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So why do we subtract the probability of A intersection B? Well, this is to avoid double counting. If we look at the two events on a Venn diagram, we'd have two intersecting circles, and the probability of A union B would be this green shaded region. And the individual probabilities, so the probability of A would be this green shaded region, and the probability of B would be this green shaded region. And you'll notice when looking at the individual probabilities of A and B, we've included the intersection of A and B for each of the individual probabilities. And so it's been counted twice. So we have to remove one occurrence. And that's why we subtract the probability of A intersection B. And so if we plug the given probabilities into this equation, we have the probability of A, which is 0.4, plus the probability of B, which is 0.35, minus the probability of the intersection of A and B, which we're given as 0.14. And if we calculate this, we get the probability of A union B equals 0.61. In our second question, we have a class of 40 students. 20 play football, 18 play basketball, 16 play tennis, 8 play both football and basketball, 7 play both football and tennis, 6 play both basketball and tennis, and 3 play all three sports. Part A of the question asks us to draw a Venn diagram showing this information. Part B asks us to find the number of students who play none of the three sports. And Part C asks us to find the probability a student plays tennis given that they play basketball. If you'd like to play along, pause the video now. And so looking at Part A, we have a three-circle Venn diagram, and all circles intersect. So let's start by filling in this information. We'll begin at the center, which represents those students that do all three sports. And we're told 3 students do all three sports. So I've placed the number 3 in the green shaded region. We're also told that 8 students play football and basketball, which is represented by the green shaded region on the Venn diagram. But to determine how many of those just play football and basketball, we need to subtract 3, which represents the students that play all 3 sports, from 8. And this gives us 5. And the number 5 goes in this green shaded region. We're told that 7 students play football and tennis, and this is represented by the green shaded region here. But to determine how many of those just play football and tennis, we need to subtract the number 3, so that's students that do all sports, from 7. And this gives us 4. So I've placed the number 4 in the green shaded region. And then we're told that 6 students play basketball and tennis, so this green shaded region here. But to determine those students that just play basketball and tennis, we need to subtract 3, which is those students that do all 3 sports, from 6. And this gives us 3. And I've placed this number in the green shaded region. And we're told that 20 students play football, and this is represented by the green shaded region. To determine those that play exclusively football, we need to subtract the numbers 3, 4, and 5 from 20. And this comes to 8. So I've placed 8 in the green shaded region. We're told that 18 students play basketball, represented by the green shaded region. To determine those that exclusively play basketball, so the green shaded region shown here, we need to subtract the numbers 3, 5, and 3 from 18. And this gives us 7. And I've placed the number 7 in the green shaded region. We're told that those students that play tennis is equal to 16. And this is represented by the green shaded region. And to find those students that exclusively play tennis, we need to subtract 3, 4, and 3 from 16. And this gives us a value of 6. And I've placed this number in the green shaded region. And so to find the number of students who play none of the sports, so the green shaded region on the Venn diagram, we need to subtract all the numbers in the circles from the total number of students, which is 40. So we subtract 6, 3, 3, 4, 7, 5, and 8 from 40, and this gives us 4. So there are 4 students that don't take part in any of the sports. And I've placed this number in the green shaded region. And for the last part of the question, we're asked to find the probability a student plays tennis given that they also play basketball. So this is a conditional probability question. And we have a formula for this. It's the probability of the intersection between those students that play tennis and basketball divided by the probability of those students that play basketball. And to find the probability of the intersection between those students that play tennis and basketball, we need to look at the numbers that play both. So I've marked the green shaded region as those students that play both tennis and basketball. So we have a total of 6 students that play both. And we need to divide this by our sample space, which is 40. And then to find the probability of a randomly selected student playing basketball, we need to look at the numbers that play basketball. So the green shaded region on the Venn diagram represents those students that play basketball. And if we sum the numbers in this region, we get a value of 18. And if we divide this by a total sample space of 40, we get this probability. And simplifying this fraction, we get the probability that a randomly selected student plays tennis given that they play basketball is equal to 1/3. In this next question, we're told that a disease affects 2% of the population. A test for the disease is 95% accurate for people who have the disease and gives a false positive result of 3% for those without the disease. Part A of the question asks us to draw a tree diagram to represent the information. Part B asks us to find the probability that a randomly selected person tests positive. And Part C asks that given a person tests positive, find the probability that they have the disease. If you'd like to play along, pause the video now. And so for Part A, we need to draw a tree diagram. So we're told that a disease affects 2% of the population. And so the probability of someone having the disease in a population is 0.02 or 2%. And therefore, the probability of not having the disease is 0.98, as this is the complement of having the disease. And then if someone has the disease and takes a test for the disease, then the chances of testing positive are 95% or 0.95. And therefore the chance of testing negative is the complement of this. So it's 5% or 0.05. So these probabilities are conditional upon having the disease. We're also told that the test gives a false positive result. So for those people not having the disease, 3% of them will test positive. And therefore, for someone not having the disease, there's a probability of 0.03 that they'll test positive. And therefore, the probability of testing negative if they don't have the disease is 0.97, as this is the complement of testing positive. Now we have our tree diagram. Let's look at Part B of the question, which asks us to find the probability that a randomly selected person tests positive. If we look at our tree diagram, there are two ways of testing positive. So you can have the disease and test positive, so this branch of the tree, or you can not have the disease and test positive, so along these branches of the tree. So the probability of having the disease and testing positive is 0.02 multiplied by 0.95. And as this is either or, we need to add the probabilities. So plus the probability of not having the disease and testing positive is 0.98 multiplied by 0.03. And if we calculate this, the probability of testing positive is 0.0484. Now let's look at part C of the question, which says, given that a person tests positive, find the probability that they have the disease. So this is a conditional probability question, which is asking us to find the probability that a person has the disease given that they test positive. And we have a formula for this. It's the probability of the person having the disease multiplied by the probability that a person tests positive given that they have the disease, divided by the probability of testing positive. So let's pick some of these probabilities off the tree that we've drawn. So the probability a person has the disease is 0.02, and the probability that a person tests positive given that they have the disease is 0.95. And we divide this by the probability that someone tests positive. And this is the probability that we calculated in part B. So we know that this is 0.0484, and this fraction equals 0.39. So the probability that a randomly selected person has the disease given that they test positive is 0.39. So in this fourth problem, we have a biased coin, which gives the probability of a head as 0.3, and the coin is tossed 3 times. Part A of the question asks us to draw a tree diagram showing outcomes and probabilities. Part B asks us to find the probability of getting exactly 2 heads, and part C asks us to find the probability of getting at least 1 head. And if you'd like to play along, pause the video now. So this is our tree diagram based on the coin being flipped 3 times. Each time the coin is flipped, the probability of getting a head is 0.3, and therefore the probability of getting tails is 0.7. Now these are independent events, so each time the coin gets flipped, the probability of getting a head is still 0.3, and the probability of getting a tail is 0.7. And as you can see, we have 3 levels of the tree diagram, one to represent each flip of the coin. Part B of the question asks us to find the probability of getting exactly 2 heads. So there are a number of ways this can be achieved. So when we flip the coin for the first time, we can flip a head, and then we can flip another head, but then we have to flip tails. So this branch of the tree diagram. So this is 0.3 squared multiplied by 0.7. Or the first flip of the coin gives us a head, the second flip of the coin gives us a tail, and then the third flip of the coin gives us another head. And because this is either or, we add the probability. So we have 0.3 squared again, multiplied by 0.7. And the other way of flipping exactly 2 heads would be on the first flip to get a tail, and the second and third flip to get heads. So this again would be 0.3 squared multiplied by 0.7. And once again, we add this probability to the others. And if we calculate this, we get 0.189. So the probability of flipping exactly 2 heads is 0.189. And part C of the question asks us to find the probability of getting at least 1 head. So when we flip the coin 3 times, that's the probability of getting 1 head, or 2 heads, or 3 heads, as they all satisfy the probability of getting at least 1 head. So let's look at the individual branches of the tree diagram and see which ones satisfy this. In fact, nearly all of them do satisfy this, as we'll see. If we flip 3 heads, so this path here, the probability of doing that is 0.3 cubed. We can flip 2 heads and a tail, so this path here, and the probability of doing that is 0.3 squared multiplied by 0.7. or we can flip a head, then a tail, and then a head. So this path here, and the probability of doing that is 0.3 squared multiplied by 0.7. And then we can flip a head followed by 2 tails. So this path here, and the probability of doing that is 0.3 multiplied by 0.7 squared. Then we might flip a tail first, followed by 2 heads. So this branch here, and the probability of doing that is 0.7 multiplied by 0.3 squared. Then we might flip a tail, a head, and then a tail. So this path here, and the probability of doing that is 0.7 squared multiplied by 0.3. And then finally we could flip a tail, followed by another tail, and then a head. So this branch here, and the probability of doing that is 0.7 squared multiplied by 0.3. And as you can see, the only path that doesn't give us what we want is this one, where we flip a tail, followed by another tail, followed by another tail. All other paths give us at least one head. And when we sum these probabilities together, we find that the probability of getting at least one head is 0.657. In this video, we're going to look at a series of exam-style probability questions, and I'll show you the exact step-by-step methods to solving them. In the first of these, we're told that a standard pack of playing cards is shuffled and one card is drawn at random. That event J equal the card is a jack, and event H equals the card is a heart. Part A asks us to find the probability of the intersection between J and H. Part B asks us to find the probability of the union between J and H. And Part C asks us to state with reason whether J and H are mutually exclusive. And finally, Part D asks us to state with reason whether J and H are independent. If you'd like to play along, pause the video now. To help us solve this question, I've created a 2-circle Venn diagram. The first represents event J, where the card is a jack, and the second represents event H, where the card is a heart. So let's start filling in the numbers here. So in a pack of 52 cards, there is only one jack of hearts. So I've placed the number 1 in the intersection between the card being a jack and the card being a heart. And in total, we have 4 jacks in a standard 52 pack of cards. Now we know one of the jacks is a heart, and we know that 3 are not hearts. So we place the number 3 in the part of the Venn diagram that represents jacks but not hearts. So the sum total of jacks is 3 plus 1, and that equals 4. We also know that there are 13 hearts in a pack of 52 cards, and we know that 1 is a jack of hearts, which we've accounted for. So I've placed the number 12 in this region of the Venn diagram, and it represents those cards that are hearts but not the jack of hearts. And finally, we know that there are 52 cards in the pack, so those cards that are not jacks or hearts is equal to 52 minus 3 minus 1 minus 12, and this equals 36. And this number we place outside of the 2 circles, but within the rectangle. And part A of the question asks us to find the probability of the intersection between jacks and hearts. And we find this probability by taking the number 1 that appears in the intersection between J and H and dividing it by the total sample space. So we have the probability of the intersection between J and H is equal to 1 divided by 52, which is the total number of cards in the pack. And for part B, we're asked to find the probability of the union between J and H. Now we can use the addition rule to find this probability. And the addition rule tells us that the probability of the union between J and H is equal to the probability of J plus the probability of H minus the probability of the intersection of J and H. So let's calculate the individual probabilities. So the probability of a card being a jack, given that there's 4 jacks in a 52 card pack, is 4 divided by 52. And the probability that a card is a heart, when there are 13 hearts in a 52 card pack, is 13 over 52. And we know the probability of the intersection between J and H, as we've already calculated it, and it's 1 divided by 52. And plugging these probabilities into our equation, we have 4 divided by 52 plus 13 divided by 52 minus 1 divided by 52. And this equals 16 divided by 52, or 4/13. And this is the probability of J union H. Now, part C of the question asks us to state with reason whether J and H are mutually exclusive. Now, for them to be mutually exclusive, it means that they cannot happen at the same time. So if they were mutually exclusive, the probability of the intersection between J and H would equal 0. And we've calculated the probability of the intersection between J and H, and we found that it was 1 divided by 52. And this is not equal to 0, and therefore the events J and H are not mutually exclusive. And for part D of the question, we're asked to state with reason whether J and H are independent. So if they are independent, it means that the outcome of one does not have any impact on the outcome of the other. And we know that the probability of J and H is equal to the probability of the intersection between J and H, which is equal to the probability of J multiplied by the probability of H. Now, we've already calculated the probability of the intersection between J and H, and we found that it was equal to 1 divided by 52. And we also know that the individual probabilities, so the probability of J is 4 divided by 52, and the probability of H is 13 divided by 52. And when we multiply the individual probabilities together, we get a value of 1 divided by 52, which is the same as the probability, the intersection of J and H. This means, therefore, that the events J and H are independent. In our second question, we're told that we have a box that contains 4 working batteries and 2 faulty batteries. 3 batteries are selected at random, one at a time, without replacement. In part A of the question, we're asked to draw a tree diagram representing this information. In part B, we're asked to find the probability that all 3 batteries selected are working. And in part C, we're asked to find the probability that exactly one of the 3 selected batteries is faulty. If you'd like to play along, pause the video now. And so for part A, we're asked to draw a tree diagram representing the information. So we have a box containing 6 batteries, and we know that 4 are working and 2 are faulty. So when we make our first selection from the box, there's 4 chances in 6 that the battery we select is working. And as such, there's 2 chances in 6 that the battery we select is faulty. Now for our next selection, the question says that we make our selections one at a time without replacement. So when we make our second selection, there are only 5 batteries in the box. And if our first selection was a working battery, there are now only 3 working batteries in the box. So in our second selection, there'll be a 3 in 5 chance of it being working. And as there are still 2 faulty batteries in the box, there'll be a 2 in 5 chance of our second selection being faulty. And if our first selection was a faulty battery, there'll still be 4 working batteries in the box. So the chances of selecting a working battery in our second selection will be 4 chances in 5. And the chances of selecting a faulty one will be 1 chance in 5. And then on to our third selection, there are now only 4 batteries left in the box. If our first 2 selections were working batteries, there'll still be 2 working batteries left in the box. So the chances of selecting a working battery will be 2 in 4. And similarly, there'll still be 2 faulty batteries in the box. So there'll be a 2 in 4 chance of selecting a faulty battery. If our first selection was a working battery and our second selection was a faulty battery, that would mean that there are still 3 working batteries in the box out of a total of 4. That means the chances of our third battery being a working battery is 3 chances in 4, and 1 chance in 4 of it being faulty. If our first selection was a faulty battery and our second selection was a working battery, then there'd still be 3 working batteries left in the box out of a total of 4. So the chances of our third selection being a working battery would be 3 chances in 4, and the chances of it being faulty would be 1 in 4. And if our first 2 selections were faulty batteries, that would mean that there are no faulty batteries left in the box. So we're guaranteed to select a working battery in this case. There'd be 4 chances out of a total of 4, and therefore the probability of selecting a faulty battery would be 0, because there aren't any faulty batteries left in the box. In part B of the question, we're asked to find the probability that all 3 selected batteries are working. So if we look at our tree diagram, this would mean that the first battery selected would be working, the second battery that we selected would be working, and the third battery we selected would be working. And so if we pick the probabilities of the branches I've marked, the probability of this happening would be 4/6 multiplied by 3/5 multiplied by 2/4. And this would equal 24 divided by 120, which simplifies to 1/5. So the probability that all 3 selected batteries are working is 1/5. In part C of the question, we're asked to find the probability that exactly 1 of the 3 selected batteries is faulty. Let's take a look at our tree diagram and look at the possibilities. So if the first battery selected is a working battery, and the second battery selected is a working battery, then the third battery must be faulty for this situation to exist. So we can multiply these probabilities together. So we have 4/6 multiplied by 3/5 multiplied by 2/4, and this equals 1/5. In another scenario, the first battery selected can be working, the second battery selected can be faulty, and then the third battery selected must be working for this situation to arise. So if we multiply these probabilities, we have 4/6 multiplied by 2/5 multiplied by 3/4, and this once again equals 1/5. And if the first battery selected is faulty, then the next 2 selections must be working batteries for this situation to arrive. So this path followed by this path. And multiplying these probabilities together, we have 2/6 multiplied by 4/5 multiplied by 3/4, and this again equals 1/5. So as we can choose any of these 3 paths to select one faulty battery, so either path 1 or path 2 or path 3, we need to sum the 3 probabilities. So we have 1/5 plus 1/5 plus 1/5, and this equals 3/5. So the probability that exactly one of the 3 batteries selected is faulty is equal to 3/5. In our third question, we're told that for events A and B, the probability of A is 0.5, and the probability of B is 0.3, and the probability of A union B is equal to 0.65. Part A of the question asks us to find the probability of A intersection B. Part B asks us to draw a Venn diagram labeling each region with its probability. And Part C asks us to find the probability of A given B. If you'd like to play along, pause the video now. Now for Part A of the question, we want to find the probability of A intersection B. And to do this, we can use the addition rule. So using the addition rule, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Now we already have the probability of A union B and the probability of A and the probability of B. So we can solve this equation to find the probability of A intersection B. So plugging in the probabilities given in the question, we have the probability of A union B is 0.65, the probability of A is 0.5, and the probability of B is 0.3. And rearranging the equation gives the probability of A intersection B equal to 0.5 plus 0.3 minus 0.65. And this equals 0.15. For part B, we're asked to draw a Venn diagram and label each region with its probabilities. So here I've drawn a Venn diagram with 2 circles, one representing A and one representing B. And the probability of A intersection B, this green shaded region, we calculated in part A of the question, and this is equal to 0.15. The green shaded region on the board shows the probability of A only. So that's exclusively A, and it's the probability of A minus the intersection of A and B. So that's 0.5, which is the probability of A, minus 0.15, which is the probability of A intersection B. And this gives us a probability of 0.35. And the probability of B only is this green shaded region. So the probability of B only is equal to 0.3, which is the probability of B, minus 0.15, which is the probability of A intersection B. And this gives us a total probability of 0.15. Everything outside of the circles represents the probability of not A union B. And to get this, we can subtract A intersection B, A only, and B only from 1. And this gives us a probability of 0.35. And for part C of this question, we want to find the probability of A given B. So this is a conditional probability question. And the way we find this is we take the probability of A intersection B and divide it by the probability of B. Now we calculated the probability of A intersection B in part A of the question, and we saw that that was equal to 0.15. And we're given the probability of B, which is 0.3. So the probability of A given B is 0.5. And you'll note that this probability is the same as the probability of A. So this means that the events A and B are independent events, as the probability of A given B is equal to the probability of A.